All right. All right, everyone, welcome. Today we'll be going over deep neural networks. We'll start off by doing a small recap of last week, and then we'll go into more a bit about how we choose different parameters when building neural networks. So to get a quick raise of hands of who here or who was here last week, we went over neural networks. Okay, a little bit, perfect. We'll spend a little bit more time on the recap. Everyone, you should get caught up. If you have any questions, which I am expecting a lot of, please raise your hand and I will hopefully answer it and clear up some of the different questions everyone has. All right.
So before we get started, I have the limit challenge again. This time it's some presentations again on the final meeting of the year for the quarter, which is going to be Tuesday, March 12th. This means that the submission deadline is 11 p.m. on Sunday, March 10th. Gives us Monday to submissions, etc. And then this time the workshops are on Thursdays from 3 p.m. to 5 p.m. Again, there will be 2 workshops every time, a kind of catch-up workshop and a main one covering stuff. I'm going to be doing them covering slightly different stuff, just kind of a different approach. So if you're really happy with PyTorch, if you're like that stuff, we'll still support that by a slightly different avenue to kind of go about things. Maybe you want something different. So, without further ado, let's go ahead and reveal the theme for this quarter size no limit challenge.
Oops.
Backwards. There we go. Back to square one. So that's the theme for this quarter size no limit challenge. Back to square one. That can be again interpreted however you can justify it. Not here a plug Ouroboros, just for some inspiration. And yeah, I hope you guys have some fun with this. Posting guidelines. It's not.
Cool. So a lot of people here who wasn't here last week, so we'll cover a little bit about the basics of neural networks, how they work, a bit about the calculations and the math behind it. But don't worry, we won't go too deep into the math because let's be honest, we're not all here to get another math lecture. So some basic overviews of a neural network. Neural networks are a series of interconnected layers where the number of layers represents the depth of a neural network. So the diagram over here, it's kind of from the left to the right, number of layers is the depth. Each layer consists of multiple neurons, where each neuron is calculated using information from a previous layer, stores a value, which is then used to calculate the next layer. So the number of neurons per layer is considered the width. So here we have the width and the depth of our neural network. Neural networks also include an input layer and an output layer. So the input layer would be all the data that you are giving to the neural network. So for instance, if you're trying to give it a picture, maybe all right, cool. We'll use this. So a little bit about the calculation. So this is one way of looking at a neural network. And so what we look at here, we want to see those inputs. So remember the inputs from the previous slide, how I told you every neuron is calculated using the neurons from the previous layer. So for instance, the 2 here is calculated using some combination of every single one of these inputs from the previous layer. So going back to the diagram from the next page, this is how we actually get that value. So again, the values might be a little bit different, but don't worry too much about it. So we start off by adding or multiplying every single one of these inputs by a weight value. For now, these are just arbitrary values that will then get trained when we go to fit our neural network to the data. So don't worry about how we get those values yet, but just know we multiply each of these input values by some arbitrary weight. We add them all together with some bias value, which again is also some arbitrary value that will then get trained when we fit our model to some data set. And then we throw it through an activation function. This could be a lot of different things, sigmoid, linear, tanh. Don't worry about that. We'll get to that later. But once you do all of that, you'll get to our output, which in this case could be 0.1. And so that would be the value of the next neuron. So you do that for every single neuron in the layer, calculating it using the previous layer's inputs with some arbitrary weights, some arbitrary bias, put them together and throw it through an activation function. Boom, that's how we get our value of the neuron. I don't expect you guys all to memorize it, nor do I expect you guys to memorize it by the very end, but we'll just try to get a sense of understanding as we continue with these slides. So here we have an example neural network. So as we see here, it's a pretty small network. We can't really use this for anything, but as we see here, we have our input layer, which is of size 3. So we're taking in 3 things. Our output layer, which is of size 1, because we're only outputting a single value. A hidden layer, which is the layers between the input and output that are used in the calculation. So we can go first and look at how to calculate this value here. So in our case, we're going to be using a linear activation function. So f of x is equal to x, which doesn't really do anything. And we'll talk about why that's a problem later on. So if we use these weights here, so for instance, we use a 0.2 on the top neuron, 0.66 on the middle neuron, and a ×2 on the bottom neuron. So again, if we remember the equation from before, we multiply the weight values by each of the inputs, add them up, plus the bias. In our case, the bias is -2. We get the value of the neuron after throwing it through that activation function, which in this case is linear, doesn't affect it. So can anyone tell me, do the quick maths of what this neuron should be equal to? So again, you can follow the formula up here or this one down here. Or on the board. Yes. 1. Iron Mouse, I don't remember. Did you already calculate this value? Yeah. Anyway, so yeah, well, you can't calculate this one or this one yet. So anyway, so the way we're able to get 5 is what we do is we multiply 5 by 0.2, that's 1. We add that to 3 times 0.66, so that's 1 plus 2. And then 2 times 4 is 4, so we do, what is this? 3 plus 4 is equal to 7, and subtract by 2, and that's how we get 5. Does everyone get that so far? All right, let's try the next one. So now we have our weight value of 0.4, 2, 3 with a bias of -10. Can anyone tell me the value of the neuron here? Want to take another shot at it? 4. Do you guys agree with 4? I actually don't. No. Take a raise hand if you think it's 4. All right, no one's really confident. Anyone else want to take a... I'm just going to put the next answer. Answer is 4. You got it right. Perfect. Don't worry about it. So if we look at the math, again, 0.4 times 5 is 2. This is 6. This is 6. That's 12 plus 2 is 14 minus 10 is 4. It's okay if you don't want to do that really quick, but you guys understand the general calculations of this. So if we keep going, you don't have to calculate this, but we can see that, hey, our weights can also be negative values. A bunch of different things can happen with our bias plus 3. This one will get us to a neuron score of 1. So now we have all the values in that first hidden layer. So that with that, if we want, we can also calculate the last layer. I'm not going to make you do this, but the end goal was 1, which is why I was surprised when you said 1. You got it right. But one interesting thing is through this, we went through these complex, or I guess not too complex, calculations to build our neural network to get to our final value. And so the goal of the neural network is then to figure out what weight values and bias values are the best for predicting whatever you are doing. So for instance, maybe if you are building a predictor that tries to identify a picture of a dog, whether something's a dog or not, maybe it turns out this weight value is better as a ×2 instead of a ×0.5. How it decides that, we'll get that into there in a second. But does everyone have a decent understanding about how the math of it works. Decent. If you're completely lost, please raise your hand and ask questions. But as long as you guys get a general idea of, you have to know all the values previously, plus the weights and biases to get to the next value. That's kind of the main idea here. To get thumbs up, thumbs middle, thumbs down about how we feel about this so far. Cool. I see a good number of thumbs up, a little bit of some middle, but no thumbs down, which is a good sign. So let's move on. So as I mentioned before, there arises a problem when you have a linear activation function. So as I mentioned, activation functions can really be anything, but if we use a linear activation function, so as we saw, it was a very simple calculation, we get to the linearity problem. So think about this in a different context where we have two linear functions, f of x and g of x. These both look pretty simple, right? You just have these constants with one's a coefficient, one is a constant that's like an intercept. So think of y equals mx plus b. Well, if we take the composite of these two, so f of g of x, so you just plug in g of x into f of x, you can then simplify this out and we get something that looks very similar to our original problem. Because if you notice, this problem right here is a linear function. And so if we really want to, we can simplify that composite function back into the original linear function itself. And so because of that, if we have a linear activation function, if we go back to here, we can actually calculate equivalently this final neuron without the use of all these middle terms. If you want to look at the math behind it, here it is. I don't expect you guys to really read this or fully understand it, but just know that once we go through all this math, we can just simplify it back into a single layer. So the reason that we want to use a non-linear activation is to not have this problem where we have composite functions become even more complex systems. Because the problem is that linear functions cannot represent everything. For instance, if you are trying to predict a exponential growth, you can't do that with a linear function. But if you took a bunch of composite non-linear functions, it adds some complexity and maybe can better encapsulate a non-linear system. So if you ever wonder why we need to use activation functions, it's to solve this linearity problem. That was a bit confusing, so if you have any questions, please let me know. Anyone have any questions? How are we feeling about this one? It is a bit more complex, so you don't expect everyone to kind of fully grasp the math behind it. Yes, question. So yes, the activation function will also help configure the domain. That's a little bit more important for the final layer. So for instance, if you're predicting a probability, you'd want to use a activation function such that the range was between 0 and 1. However, maybe in the middle of your hidden layers, you don't necessarily need those values between 0 and 1. Sometimes you might, depends on the problem. We'll go a bit into how to choose activation functions, why some are better than others a little bit later. But again, the main idea is if you take composite linear equations, you still get a linear equation, which doesn't have enough complexity to map more complex problems. I guess some thumbs up, thumbs middle, thumbs down. I know this one's a bit harder. It's okay if you don't fully understand this one. But thumbs up if you just get a general understanding of the fact that composite linear functions is not very good for moments. All right, some thumbs middle. If we have time, we can come back to this one, but I don't expect us to have too much. Cool. So activation functions, here's some example of activation functions. Again, we'll go over a little bit later about when to choose each. So you have a basic sigmoid function. If you've seen this before, this is a function where the range is between 0 and 1. Tanh, range is -1 to 1. ReLU is pretty simple. It's a max of 0 and x, so 0 and all positive values is the range, and a couple other popular ones. All right, when we talked about changing those weight functions to get a better classifier, there has to be some sort of way to measure how well is our model actually doing. So here's an example of a data set used. So it uses all of this information as kind of the inputs, and then it has a predicted income, so that's what we're trying to do, and the true income. So given these values here, can anyone tell me one way of measuring our performance? So for instance, here it got it correct, here it didn't get it correct, here it got it correct, not correct, not correct. Anyone want to give me an example of how we can measure performance? Here. Yep, that's a perfect way of doing this. So for instance, if you see here, there's 10 samples I've shown you, and it got 7 out of the 10 correct.
So we could just say maybe its accuracy is 0.7, something pretty standard. But not always is it correct or not. Sometimes you have to measure about how close did we actually get our answer to our predicted answer to the true answer. So that's considered like a regression problem, as we see here. So for instance, if we look at this graph on the right, these dots are the true values, and then this line is our prediction. So as we can see, you can't just say, hey, how many times did it actually match up? Because otherwise it's not perfect. It got 0 out of 0. It wouldn't make sense to call it a perfect prediction. So there's a bunch of different loss functions, they're called, or error functions or risk functions, all the same thing, about how to identify how well a model has performed. The most common one that we'll talk about is mean squared error. It's this function here. So we take every single point and compare it to how close it was to our prediction. We square that and find the average of those. So each of these are called residuals. You don't have to know all these terms, just the general sense of it. Take how far the line is from the error, or how far the line is from the true value, and take the square of it, sum them all up, and then divide by the number of samples. There's other ones such as mean absolute error, where you just take the absolute value instead of square it. A bunch of different ones. Again, we'll go over this a little bit later about when to choose different things. Does everyone, can I get thumbs up, thumbs middle, thumbs down about how people feel about measuring loss, why we need to do it, and a little bit about the different complexities that can come in with that. Cool, I like that. A lot of thumbs up. All right, gradient descent. So one thing that we talked about is somehow we have to change those weights and biases to turn those neural networks into something that's not just a bunch of random number generators, right? So somehow we want to minimize the loss. So to improve performance, we want to make sure our model is as closely fits the data as possible. To do so, we want to use a concept called gradient descent, which we can think of similarly to taking the derivative of the entire model to see what direction that we need to change different things to optimize our loss or to decrease or minimize our loss. So we can kind of think of this as a graph of the value of a weight and how it affects the loss. So for instance, when our weight value is this arbitrary value, and this is our loss, pictured on this graph, in what way should we change our weight to minimize loss? In which direction? Should we move it to the left or should we move it to the right? Assuming if we change weight along the line, it follows this graph. Yes. Left. If you're facing this way, yes, left. We want to move it to left because if we look at the slope or the derivative of this line, we can see if you move it to left, it decreases our loss value. And that's essentially what gradient descent does, but in a much higher scale. Instead of looking at just one weight, we're talking thousands or even millions of weights, depending on how big our neural network is. So we can keep doing this. So now that we've adjusted our weight value, you can see we have to go calculate the derivative or the gradient descent of the entire problem again to see how we want to fully minimize our weight value to minimize loss. Can someone else give me what direction we want to move our new weight value to minimize loss? You get a raise of hand. Yes. Yeah. Yes, toward the left. Again, we want to minimize it, so we want to get it to this point. So we can keep doing that. We can keep seeing where that derivative of slope tries to get us to go. And eventually, the goal is to find the absolute minimum. Can anyone find any potential issues with this type of problem? Yes. Absolutely. It only finds a local minimum. As we can see, there's a chance it gets stuck right here. And so there's going to be a bunch of different ways that we can fix this. We'll go over that a little bit later. Concept of momentum, other different types of gradient descent methods that will help us get out of these local minimums. So sometimes if you see that your neural network is, once it's finished training, it kind of gets stuck at a certain value and it's not very good, there's a really good chance it's getting stuck in the local minimum. So you might have to tweak a couple things. And there's a couple things that we want to talk about, epochs and learning rate, which can help solve this problem. So epochs is a number of iterations. So as we saw when we moved our weight value, we only moved it a small amount each time. So each time we recalculate it and see how that affects loss, that is considered an epoch. So we want to say, hey, this is our first epoch. Now we're on our second, third, forth, and we just keep going until we say, hey, we've converged after, let's say, 5 epochs. Another thing we can mess around with is the learning rate. The learning rate determines how much we actually want to change the weight value. So for instance, as we see here, we have a large jump when we change that weight value. That would represent a large learning rate. So for instance, if we only want to do small jumps at a time, we'd want to decrease the learning rate. Higher learning rate means larger jumps. So sometimes you might end up starting from here with a high learning rate, you might jump all the way to the other side of the curve, and then all the way back, and all the way back, and all the way back. So sometimes you want to play around with the learning rate to help you get to that absolute minimum, because again, sometimes you might find a local minima, which can be a problem when you're trying to get the best performance out of your model. Here's a fun GIF about what that can look like. Does anyone have any questions about how gradient descent works? I'm not going to go too much into the math or the calculus of it all. Yes. All right. Excited.
This is a fun question. So basically, the idea for why you need to do any sort of learning instead of just knowing where it is because you don't know the function. That's the point of using neural networks. You don't know what equation you're modeling. That's the really cool thing. The whole idea of learning is that you're able to learn a function that isn't predefined. So if, for example, you know that you're using data that's very linear, you probably don't want to do that. But if you're working in like 12-dimensional space for your data, it's going to be very, very hard to find a concrete equation to minimize that and accurately map it. So the process of doing gradient descent allows you to approximate this. And that's a really, really cool, powerful thing about neural networks is that with a sufficiently large or wide neural network, you're theoretically able to model any equation. And so for the answer for why you can't just go to the nearest minimum is because you don't know where it is. And so by taking incremental steps, the thinking is you're going to get closer over time. And that's why learning is such a powerful and cool process. Yeah, so you know the shape of the function where you're currently at. You just don't know where it is anywhere else. It's a you know you can measure how accurate your model is on your data as you're looking at it currently, but you don't know anything else. It's a weird type of memorylessness where we aren't able to know the rest of it because we don't have the weights for every single point. So rather than just making random guesses, we can initialize somewhere and then slowly approximate over time. I hope that cleared up.
Cool. Can I get a thumbs up, thumbs middle, thumbs down about how we feel about gradient descent as a concept? You don't have to worry about the math or how it comes up with those values, but just the concept of optimizing the weight and bias values to minimize loss. Okay, mostly thumbs up. All right, your question. All right, cool. Let's move on to the quick recap just to make sure everyone has a good idea about neural networks. So neural networks are simply a system of interconnected nodes or neurons where we can get a neuron's value by using the previous layer's nodes with a combination of weights and biases, which are then trained. We can train these weight values via backpropagation or gradient descent with the goal of minimizing loss. So if you blinked out the entire time, which I don't blame you, these are the main takeaways you should get from those first slides and from last week. Cool. Oh, yes, question. Yes, weights and biases. Oftentimes biases is included in the weights. So, yeah, it is considered a weight. Yeah. All right, cool. Let's look at some code. So if everyone can get out their laptops and go to tinyurl.com/skydnn, this will get you to a Colab notebook. I gotta raise hands. Who here has used a Colab notebook before? Yes, almost everyone, I think. So please create a copy of the notebook and make sure to change the runtime from CPU to the T4 GPU that we get for free. That will help hopefully make things run faster. Not that it matters too much because these are not huge models that we are building. So you guys should all see something like this. Make sure you want to create a copy, so save copy and drive.
For when you
Thumbs
have
up.
it like open
Give me a
successfully.
thumbs up. When we go to runtime, we want to change the runtime type to T4 GPU. Let me zoom in close. Looks good now? Everyone? Cool. All right, so let's go ahead and run everything. The code should hypothetically run without any hiccups. So roll this 7. Let's keep going with the slides. So as we talked about, what neural network means. But what does a deep neural network? Well, it doesn't really mean a deep neural network. It just means multiple layers deep and tends to represent more complex neural networks. Last week, we think we played around with a neural network with a single hidden layer. No hidden layers. Yeah, last week we didn't do any hidden layers. So this time we'll be talking a little bit more about hidden layers, how many hidden layers we need to use, and what size, the width, depth, different things we can play around with to help really optimize. Don't think we'll have time to go through all of them, but yeah.
If you're having troubles with the, go ahead and raise your hand.
Cool. So let's see if the notebook has run. Oh, it's still running. All right, cool. Yeah, keep it. So if everyone can scroll down a bit, we start off with importing everything we need to use. So the main thing we want to take away is we'll be using TensorFlow Keras, which is an API for building neural networks. You'll use that a bunch, so hopefully you get it sometimes. This first, or this second code block is just downloading the data. Our data set is predicting the cover type of, I think that's some force. So whether or not that force is, I guess there's what, birch forest? What were the different data set pieces of use? The cover types, yeah, we have spruce fir, lodgepole pine, aspen, a bunch of different forest cover types with a whole lot of parameters if you really want to move into that data set. So, again, this is what the data looks like. Going to browse through that. And so then we go to actually cleaning up the data. Because when we start off with the data set is a bit unbalanced. So what different things can we do to help make our data set look nicer? This is, let me go back. So what are different ways that we can manipulate data? Models predict. Because there's a lot of different things that can happen with our data that can hinder our performance. So one thing we could do is undersampling. So undersampling is an example where if we have a lot of examples of a couple types, and we want to modify the data set, hopefully have a equal number of data points for each of the labels. So as we see here, there's not very many hamsters, but if we decrease the amount of samples in each, we can get it to be somewhat equal. So we do something similar with the data set here, where I think, I don't remember which exact cover layer, but some cover types significantly less samples. And so we limit each label to consist of a maximum of 6,000 instances, which should be about enough for stuff that we're about to do. But there's a bunch of different ways to solve this problem. In this case, we're using I'll go through this a bit quick because we want to cover a little bit more about neural networks. Another thing we want to do is we want to do data normalization. So there's a bunch of different ways of normalizing our data. We just want to make sure our data is presentable well for everyone. If you really want to talk about the math behind it, neural networks perform better when our inputs are between values of 0 and 1 rather than the original starting values, which could be 0 to 1,000. Different ranges. So in our case, we'll just be using scaling to range. So switch it to between 0 and 1. If you want to look at the code about how that works, you can. I'm not going to worry too much about it right now. Another thing that is important to do is splitting our data into training and testing data sets. Additionally, if we want to do a foundation set, but I don't think we do that here. What we want to do is we want to split this data because if we don't, we can incorporate some sort of model. We don't want our data set, our model to memorize the data set, and therefore when we try to test on new data, it will just perform poorly because we memorize data set, learn the data. I don't know if you've ever heard your language classes don't memorize. I don't know if you guys, that's just my experience. So we want to use our training data to train the model, and a separate data set, which is our testing data set, is used in the final evaluation. Again, you can use a validation set, which can be used to modify the parameters. Not going to worry about that. So let's go ahead and look at how we actually build a neural network. So as we see here, we want to define a pretty deep neural network just to start. So as we see, we have a bunch of inputs. In our case, we want a input size of, I think we'll say 54, because if we look at the data set, we have a data set size 54. We start off by saying, let's add a new layer that has an input shape of 54. And then we'll say, hey, our first layer, let's just call it of size 10. It's just some arbitrary value. We choose whatever we want. Talk about later about how we choose the values. We'll give it an activation function, the sigmoid function. Again, we'll talk about that later. Let's just throw in a bunch more. Call it add a new layer of size 20, another layer of size 100, 50, 40. Throw it all together, and we can build that model. And it'll look something like this that we have here. So if we go scroll down, we can see how it actually works. So we build it. It shows about what it will look like. And by the way, a dense layer just means it's fully connected. So every single neuron is connected to every other neuron. There's other types of different layers that we'll cover later, like convolutional. A bit different, but what we covered are dense networks. So don't have to worry about too much. Another thing we want to look at is the loss function and optimizer. In our case, we'll be using stochastic gradient descent, which is just gradient descent, but with samples. We don't have to worry about too much what that means with a linear rate of. Our loss function are mean squared error. We talked about this earlier. Don't worry about these values. We'll play with them later. We set an epoch to be 30, and we can compile and fit our model. So we'll train for 30 epochs and slowly, hopefully, get a little bit better over time. So as we can see, after 30 epochs, we have an accuracy of 68%, which when we're predicting out of 7 things, I'd say is pretty decent, right? Could be better. And so let's look at the different ways that we can improve it. So if you want, you can also scroll down and see a bit how we change over time. If you have time, we can cover those later. Let's get back to this. So one very common problem that we could see with models is a concept called overfitting or memorizing the training data. If you can see, there's a bunch of about want to learn the data, not memorize it. Underfitting, or it'd be a case where it doesn't actually learn the data, as we see. Overfitting would be where you really are fitting your data too tightly. You just want to learn a general trend rather than kind of doing appropriate fit would just be it might not be perfect again. Perfect. So how can we fix this problem? There's a lot of different ways. One thing, we could just have more data. More data that we have will tend to have a less issues with overfitting. However, very rarely will you just say, oh, I want more data and just get more data. Oftentimes, that is a very large limiting factor. So other things you can do is reduce the complexity of the model. So for instance, if you have a less complicated model, it can't create more complex predictions. So if you reduce the number of layers or reduce the number of nodes, so for instance, decrease the width or the depth of the model, you can make your models less complex, or you can also just train less times or decrease the number of epochs. Sometimes that works, sometimes doesn't, mostly around learning rate. And finally, you can do this concept called dropout. Dropout randomly selects neurons and will zero them out. This will help with the concept of co-adaptation, where multiple neurons will learn the exact same thing. So for instance, let's say you're predicting whether pictures of a cat or a dog, and you have the third neuron, the second layer, might end up saying, hey, if I'm a 1, that means that this image has a picture of a nose or contains a nose. And maybe the neuron on the same layer, but maybe the fifth neuron also says the same thing. Well, when they both say the same thing, they create some problems, which is co-adaptation, and create biases that you don't want. Again, you want to make it less complex. If we zero random neurons out, we can help prevent this from happening. A lot of math, proofs behind it, I'm not going to go over it. But you can set a dropout rate or the ratio of neurons that we want to zero out. So in the case of 1/2, you can see your example 1/2, we just zero out half the neurons and delete half of the neurons at random. Because we're deleting half the neurons, we want to increase the value of all the remaining neurons. So you can multiply the remaining neurons by 1 over minus ratio. Don't think too much about it. For instance, if 1/2 becomes 2, 1/3 becomes 3 over 2. Don't worry too much about that. Just know if we remove neurons, we have to increase the importance of every other neurons. So how do we actually go into our model? Well, we can't see that right here, but we can add dropout pretty easily to our model. So for instance, when we go define our model above, again, I'm going to type it out. If you guys want, you can play around with where you put the dropout layers and what values or ratios you want to use here. So for instance, after maybe the second layer, so the dense 20, I'll add a dropout layer. To do that, we want to do model.add because we're adding a new layer system to our neural network. We want to add a dropout layer. So just dropout and then our ratio. Our rate, I'm going to use 0.2. You guys can play around with what values might work better or worse for you. But in my case, I'll put 0.2. If you want, you can add it in multiple places. So I guess I'll just throw it under ReLU and tanh. Might as well see how this works. Sometimes it helps, sometimes it doesn't, depending on the problems you're having. If you're not having adaptation problems, you might not need dropout. We'll see. So if I play around with these values, let's go ahead and build that model. So we have our new model. Swap out layers. And let's go ahead and fit that model. So go ahead and train it. And we'll let that be. Can I get thumbs up, thumbs middle, thumbs down about how we feel about the concept of overfitting and dropout? Thumbs up, thumbs middle, thumbs down. Yes, question. So yeah, that's a great question. I probably should. So one way to see if if your model is memorizing the train data is to check the accuracy, both your model and the train data and the test data. So for instance, if your model is 100% accurate on the training data, but then when you test it on the testing data, you see it's only 60% accurate, it's a good sign that it's probably overfit or it memorized the training data too much. But yeah, so the difference in training and testing data is like testing accuracy is a good way of identifying whether overfit data set. Cool, let's move on. So hopefully it improves. It's actually worse. I'm not going to worry about that. So when we're building a neural network, how can we decide how many layers that we want with a depth? How deep of our neural network do we want to make? If we have a very, very basic network or one that's linearly separable, basically we can create a line that's y equals mx b plus b to fit it. We don't need any hidden layers. It's a very simple design. We don't need anything special. And we could just use 0 hidden layers. However, if our data is a little bit more complex, so it's not quite linearly separable, so maybe some values depend on other values. So for instance, if we're trying to find what a good soccer player is, maybe someone that's bulky and tall is good, but also being small and fast. So maybe something like a little bit more complex than that might require an additional hidden. If you have a lot of different dimensions, so for instance, you just have tons of input parameters, you might want to look a little bit more to like 3, upwards of 5. I wouldn't really worry about going that high unless you get very, very complex situations. And again, you will almost never need to do 8 hidden layers. That will almost always lead to overfitting. So I would tend to be a bit more conservative when it comes to building the depth. And you'll see that as a common situation we'll see later. So again, there's some information. If you have too many hidden layers, they can wildly overfit your data set. So let's go ahead and remove some layers. First, before we remove some layers, let's actually look at how everyone performed. Does anyone remember if it improved or made your model worse by adding dropout? Okay, raise your hand if it improved your model by adding dropout. All right, no hands. Anyone know if it made it worse? Who here doesn't remember? Fair enough. Fair enough. Made it worse? All right. Well, let's go ahead and play around with removing some layers. If you want, let's go ahead and remove a couple layers. I'm going to remove this 100 layer. It's probably a bit much. And then let's also remove this into it. So now I have 2 hidden layers. A hidden layer of 50. The final layer needs to be of size 7 because remember, we are predicting 7 things, whether or not it's one of 7. So let's go ahead and run that. Hopefully this gets us some better accuracy. It will also train a lot faster. Now, because we're decreasing the number of layers, there's a lot less weights that we have to calculate how to change. So let's go move on ahead to width. So this is the number of neurons per layer. There is no perfect way of determining how many neurons you want per layer, but there's some general rules of thumb that we can follow. But this number tends to be between the size of your input layer and the size of your output layer. If you want, you can read a bit more rules I have up here. So for instance, our input size, what we say was 54, and our output was 70. So maybe we want to decrease this number instead of 50, maybe we can change it to 10 or 30, something like that. So we can go play around with that and decrease the number of neurons. As we see here, we can decrease the number of neurons. Some other important things we can look at is you tend to want to have much larger depth than you want to have a large width. So if you're going to have one or the other, having a larger depth is typically more important than a larger width, as when you look at the math number of weights you need to be trained, mathematically having a larger depth decreases that rather than having a larger. Another fun rule you can play around with is you want to have subsequent layers are smaller. So for instance, maybe your first in layer is the large one, maybe the next one's a little bit smaller. Again, this is one of the things you really have to play around with, get used to it, see which ones work best. So let's go look at how our model worked when we removed some layers. Did it improve? Not really. It kind of got a little bit worse. Again, these are one of these things you really have to play around with, see what the data set likes. It's very specific to you. So let's go ahead and reduce the width of our neural network. Again, you guys can play with different numbers. I will use maybe 20 and we'll go ahead and rerun that and see how it does. Yeah. So how do we feel about this so far? Yeah, thumbs up, thumbs no, thumbs down about overfitting, changing depth and width, the benefits of having complex model, consequences of it. How do we feel? Thumbs up, thumbs middle, thumbs down. All right, cool. Some thumbs up. So again, if you fell asleep during the entire thing, understand. It's lecture. It's done with. Yeah, so dropout is used for zeroing out random neurons to help prevent co-adaptation. which is when multiple neurons learn the same thing. But we also want to reduce the number of layers to help reduce the train time and overfitting. Put it between 1 and 4 layers. Reduce the size of each layer, so the width, so decrease the width to be between about the input and output size, and it is better to increase our depth than increase pressure. I think just because it adds randomness to Cool. Let's move on to the next slide. So now we want to talk about different activation. So if you remember earlier, we used the linear activation function just as a very basic way of calculating it, but the linear activation function isn't widely used. So what are the different activation functions? Well, as we mentioned, there's the sigmoid activation function, tanh, ReLU, linear, sigmoid, and softmax. I'm not going to go into the math between all of those, but if you want, you can follow these decisions to figure out which ones you might want to use. So for instance, when you're looking at the hidden layers, if you're building a multi-layer perceptron, aka a neural network or a deep neural network, you'd want to use the ReLU activation function, which we'll go into a bit why later. If you're building a convolutional neural net, which will go either next week or week after that, use ReLU. Building a recurrent neural net, you either want to look at the tanh or sigmoid activation function. That will either be in 3 weeks or 2 weeks. We're ways away from that. But if you're choosing an activation function for your output layer, it depends on what kind of problem you're looking at. If you're looking at a classification problem, so a binary classification problem would be whether or not you're guessing whether something is true or false. So for instance, is this an image of a dog or not a dog? That would be a sigmoid activation. If it's a dog or if it's not a dog. If it's multi-class classification, so are you predicting, is this a picture of a dog, a bird, a cat? You want to use softmax. Again, look at the math beyond this later. Multi-label classification. So for instance, this could be an image of a dog and a cat at the same time. That'd be an example of that. You want to use a sigmoid activation function. And if you're doing a regression problem, or for instance, if you're trying to predict a value, so if I want to guess the stock market value, that would be a regression problem. You'd want to use the linear activation. So that could be a value between negative infinity to range limits in that. Let's see, what time is it? I don't think we'll have time to go over. The overview is if you take the derivative of a sigmoid function over and over again, the value just gets smaller and smaller exponentially. So we lose a bunch of information. Because of that, we want to use the ReLU function, which is nonlinear, but we'll keep our gradient from bench. So let's go ahead and change the activation. Well, so in our case, we're doing a multi-class classification. Because again, we're trying to predict whether it's one of 7 cover types. So go ahead and change. I have frozen my screen. I also did not include it, but don't worry about that. We can go ahead and change the activation function to be ReLU for all of our hidden layers, and for our final output layer, we'd want to use a softmax. So if we look at our decision tree here, again, whether we're doing a perceptron or deep neural network, we use ReLU, and because we're doing a classification problem and multi-class classification, we want to do a softmax activation. So to do so, we just want to say set our activation function to be softmax. We go ahead and test to see how that does. Hopefully that does pretty decently. Why? But let's keep going. And I expect everyone to have different results right around different values. You can see how those change. Already, we can see it's doing pretty well. At 60 pockets, significantly higher. So, we talked about loss functions earlier. The main one we talked about was mean squared error. Mean squared error, because we are squaring the difference between the true value and the predicted value, there means there's a larger penalty for outliers. So, for instance, if you predicted the value to be 7, but turned out to be the answer was 100, that'd be a much higher penalty than mean absolute error, which we'll talk about a little bit later. Mean squared error tends to be the best loss function or most common loss function for regression problems. Again, when you're predicting the value of something. Another common one is mean absolute error, also known as L1 loss. And that is similar to mean squared error, but instead of squaring the difference, we're just taking the absolute value. So that means it's a bit more robust for outliers, where we won't penalize maybe when we guess 7 when the answer is 100 as much as the mean squared error. Another couple options are cross entropy and binary cross entropy and multi-class cross entropy. This is for predicting kind of the randomness in a situation. I'm not going to go over the math about that, but when it comes to classification problems, so predicting whether something is a dog or a cat, you tend to want to use cross entropy, and particularly binary cross entropy is better for binary classification problems. Another thing we can change is the optimizer. So as if you remember earlier, we use SGD or stochastic gradient descent. That's kind of the most basic, pretty slow methods of calculating how we should change those weights to minimize that loss. There's a bunch of different concepts. So as we mentioned, one problem with gradient descent is we can get to local minimums instead of at the absolute minimum. And so we can incorporate a concept called momentum, which does similar to what we think about what momentum is. So for instance, you roll the ball down a hill and there's a small divot, it would kind of jump out of that divot. Similar to what momentum does. There's another improvement called adaptive gradient descent, which is able to change the learning rate as you look at the different observations. Don't have to worry too much about that. There's also root mean squared propagation, also known as RMS-prop, which changes the parameters that will cause oscillation. So for instance, if you just keep going back and forth, it tries to prevent that. Do you need to know all this stuff? Not really. The main thing you want to cover is the ADAM optimizer. The ADAM, or the adaptive moment estimation optimizer, is essentially the de facto optimizer that kind of combines all the things that we listed above into a single optimizer. It's really fast, really efficient, and can converge really quickly. So that typically means we want to decrease the learning rate when using the ADAM optimizer. But that also means sometimes it converges too quickly, and so that has its own set of problems. Again, you might want to play around, but ADAM optimizer tends to be the best bet. So if you want, we can play around with that. Let's look at the results from the last test. If you look at the last test, we are getting slightly better results. Yes, 70% accuracy. Now, does anyone have anything better than 70% accuracy right now? This is the training data. Does anyone have anything better than 60% accuracy? Okay. And anyone below 60% accuracies? All right. How are we falling so far? We got thumbs up, thumbs middle, thumbs down on how we're feeling about different loss functions, optimizers. Oh gosh, I might remember activation functions. Again, you don't need to memorize it. These slides are here mostly just for reference. If you want to look at this in home, review these slides, check out when to use one versus the other. All right, so let's go ahead and change our optimizer and our loss function. So instead of SGD, we want to use the Atom optimizer, so we can change it to Atom. And because we're switching to Atom optimizer, we'd also want to use a lower learning rate because, like I mentioned, the Atom optimizer converges significantly faster. Another thing we want to do is we want to change our loss function. Because we're using cross entropy, we want to change it to categorical cross entropy. Again, I've linked all the documentation here, so you want to check those out there. So it's categorical cross entropy. And we should be able to run that. And hopefully that's gonna I need to start that over. Maybe you gotta redefine the model. So I had to rebuild the model so that we don't remember this runtime. All right, quick review of what we covered in the last 10 minutes, because it was a lot. ReLU activation function is the most common. When in doubt, use the ReLU as the activation function. If you want to go back to the slides and see what it does, it's pretty simple, but it also solves the vanishing gradient problem, which I quickly went over, so you don't have to understand that too much. But main key point, when in doubt, ReLU as an activation function. When it comes to picking loss, if you're in a regression problem where you're trying to predict a value, use the mean squared error loss. If you're trying to do a classification problem, use cross entropy as your loss calculator. When it comes to picking an optimizer, you can use the Atom optimizer as it optimizes quickly and tends to be the best for finding the absolute minimum over the local minimum. There's a bunch of other stuff that we could cover, but clearly we don't have the time. So if you want, we can probably go over a little bit of review some other week. But yeah, that's it. Does anyone have any questions about what we've covered so far? Cool. Can everyone please fill out the feedback form here? Helps us a lot to understand what we want to change in the future, what kind of events you guys like to see, and really make these events good for you. And for the future. While you guys do that, let's go ahead and look at how the neural network trained with our new model. We ended up with 0.79 accuracy, which I'd say is a huge improvement from our start, which is what? 60%. Let's be real. Let's see how it does on the actual test error. So as you see, this looks pretty good. And then our test accuracy, also we got a pretty decent test accuracy of around 80%, which is about what we saw with training accuracy, which kind of implies that we didn't have any overfitting, which is a good thing. If you want to look at how the data actually was predicted, so given the input, what that prediction was, you can look at the table below. We can also look at a confusion matrix. This basically tells us the concept of like true or false positives. This is predicted value and true value. So the chance that we predicted 0 and the value was 0 was 11%. Chance was 1. The true value is 1, was 8.92%, and so forth. You can see how it predicts it. For instance, we didn't do a very good of differentiating 2 and 5, the cover type for 2 and 5 a lot. Really want to look at what those were. You can scroll back to the top and see that we didn't do a good job with the difference between Ponderosa pine and Douglas fir. Something about those cover types were very similar. Yeah, if you want to keep playing around with this notebook, go ahead. Please practice, messing with the different models, the different things you can change about and see how accurate you can get. If you guys can beat 80%, I would love to hear about this. You got it. Yeah, I think that's it. If you have any questions, I'll be here for a little bit longer. And thank you all for coming.